Hello. In this video we will examine how students can use ClassWiz to support their understanding of matrices and how they work. ClassWiz allows them to define and use matrices of various sizes. Got our ClassWiz turned on, let's set it up. We'll be using matrix mode in this video, so choose this mode with menu and number 4. ClassWiz provides a way for students to define and use matrices. Here is an example. Let's start by defining a 2x2 matrix called A. We enter the matrix elements, 2 rows, 2 columns, and we enter the matrix elements as you can see them below here, tapping equals after each one, 2 and 3 and 1 and 5. You can use the cursor to move around if you wish, for example to correct an entry. When you've finished, tap clear. Notice the screen reminds you that you are in matrix mode. To display, edit or use matrices, start with the Option key. For example, to display matrix A, simply select it from the menu, number 3, and tap equals. When the matrix is displayed, you can move the cursor around to see individual elements in more detail at the bottom of the screen. Students can see how scalar multiplication works by trying it for themselves. For example, 6 times matrix A has the effect of multiplying each of the elements by 6. 6 2s are 12, 6 3s are 18, and so on. You can also write this without the multiplication sign, as we've done here. Similarly, matrix A divided by 5 has the effect of dividing each element by 5, as you can see. Notice in this case that the elements are mostly given as decimals. You can tap the standard to decimal key to represent them as fractions if you want. 0.2 is the fraction 1/5, and notice it's written a little differently from the normal way. Some arithmetic operations with matrices require that matrices are involved, not scalar numbers. For example, adding 4 to a matrix, let's add 4 to matrix A, will give us an error because it is only permissible for other matrices to be added to a matrix. We only have one matrix so far, but we could add it to itself. Matrix A added to matrix A, just to see how matrix addition works. And if you look here, we can see the result. Each of the elements in the result has been 2 add 2, 3 add 3, 1 add 1, and 5 add 5. Matrices can be multiplied together provided they have matching numbers of rows and columns. In this case, we only have one matrix, but we can multiply matrix A by itself, since the number of rows is equal to the number of columns. There are several ways of doing this. Here's one way. Matrix A multiplied by matrix A. Notice that the multiplication symbol was used here, but in fact it's not necessary. Here's another way. Matrix A and matrix A with no multiplication symbol, and we get the same result. The squaring key has the same effect. Matrix A squared with the squaring key here gives us the same result. But notice, however, that you can't get the square of a matrix by powering the matrix using the powering key. Option 3 to the power 2 gives an error. Let's go back to squaring the matrix the correct way, and you can notice the result is not the square. 7 is not the square of 2, and 21 is not the square of 3. So the squaring operation in matrix multiplication works differently from normal multiplication. You cannot perform division of matrices directly either, but you can use inverses to perform division, as we will see later. If we try to get an inverse, a division of matrix A by matrix A, you can see we get an error. Some square matrices have an inverse, which can be obtained in the same way that the inverse or reciprocal of a number is obtained, using the x to the minus 1 key. It's usually tedious to find an inverse of a matrix by hand, but on the class whiz, it's not tedious at all. There's the x to the minus 1 key, the inverse key, and we can see the result. Notice in this case, as we move around, that the results are given as fractions at the bottom of the screen, and curiously, each of the fractions has a denominator of 7. We'll see where that comes from shortly. To understand the idea of an inverse, multiply the matrix by its own inverse. So here's matrix A, and we multiply that by matrix A inverse. The result, as you can see, is the identity matrix, with 1s on the diagonal and 0s everywhere else. We could also multiply the inverse by the matrix the other way around. Matrix 3 inverse multiplied by matrix 3, and we get the same result. In general, matrix multiplication is not commutative. That is, the result is not necessarily the same if you multiply in a different order. But in this case, the result is the same both ways. This matrix is called an identity matrix. It's like the number 1 for the multiplication of real numbers. And as you can see, there are 1s in the diagonal and 0s everywhere else. Notice that the inverses of numbers work in a similar way. So 5 multiplied by 5 to the negative 1 gives 1 in the same kind of a way. We can get identity matrices of up to size 4 directly from the option menu. Option, move down 1, and you can see number 4 says identity, and we can choose an identity of a particular size. So let's choose an identity of size 3, and there's the identity matrix of order 3. All the diagonal elements are 1s and everything else is a 0. If you multiply a matrix by the appropriate identity matrix, then the result will be unchanged, which is similar to multiplying a number by 1. For example, matrix A we'll multiply it by the identity matrix of the correct order, which in this case is order 2. And you can see the result is the same as matrix A. It's like multiplying a number by 1. Nothing happens. Matrices with the same dimensions can be added or subtracted together, as you saw earlier. So we could add matrix A to the identity matrix of order 2. They've both got 2 rows and 2 columns. And if you look at the result, you can see that the 1 has been added to 2, 1 has been added to 5 to make 6, and these have stayed the same. So the elements in the same place have been added to each other. Each element of the new matrix is the result of adding the corresponding elements of the 2 matrices. A square matrix has a determinant, which is a number that is usually tedious to find by hand, especially for larger matrices. On the class whiz, the determinant command is in the second page of the option menu. Go down to the second page, number 2 says determinant, and we need to say determinant of a particular matrix. Again, we'll use our matrix A, and the determinant is a number. In this case, the number is 7. And you might remember earlier that was the number that was the denominator in the inverse of matrix A. So determinants are important for finding inverses. For some purposes, a transpose of a matrix is useful, switching the rows and the columns. This is also obtainable from the option menu. transposition, which is number 3, and the transpose of the particular matrix, in this case of matrix A. And if you look at the result, you can see that the diagonals have stayed the same, but these elements 1 and 3 have been switched from here. So what used to be the first column is now the first, this used to be the first column, now it's the first row. And what used to be the first row is now the first column. A matrix can be edited after it is defined from the option menu. For example, we could edit matrix A. Let's look at the edit matrix is number 2. Edit matrix A, number 1. And change the second row to be 4 times the elements in the first row to illustrate how we can edit. So 4 2s are 8 and 4 3s are 12. So now we've changed matrix A, and this change will result in a determinant of 0. And considering that the determinant is used in finding the inverse of a matrix, it's not surprising that the edited matrix no longer has an inverse. So matrix 3, if we find the inverse now, we'll get an error because the determinant has been changed to 0. So we will edit matrix A again and change it back to its original values. So we don't have that problem again. 1 and 5. That completes our look at what ClassWiz offers students to deal with a single matrix. Students can experiment for themselves with other matrices of their own choice to see and understand the effects of various operations and commands. But now it's time to use more than a single matrix. So we'll define another matrix called B, this time with 2 rows and 3 columns. So the dimensions are 2 by 3. Here's what we'll do. So to define the matrix, we will say define matrix number 1. And the number of rows here is 2 rows. And the number of columns is 3 columns. We put the elements in the matrix as we did before. 4, -1, 2, 7, 2, and -5. So there's our matrix B. We can recall the matrix as with matrix A to check that it's correct. And there it is on the screen. And then we can use matrix B and matrix A together in various ways. With a pair of matrices, students can experiment to check their understanding of the various matrix concepts and operations. Scalar multiples are always possible. So let's get a scalar multiple of matrix B. 5 times matrix B, you notice that each of the elements is 5 times the original elements. But only square matrices can be squared. So let's see how that works. If we square matrix B, which is not a square matrix, we get an error. Also, only square matrices can have a determinant or an inverse. So if we get the determinant of matrix B, we'll see that, again, we have an error. And similarly, if we try and get the inverse of matrix B, with the inverse key, we also get an error. But all matrices can have a transpose. In this case, the transpose of B will have dimension of 3 by 2, as the rows and columns will be reversed. Let's look and see how that works. Go down to transposition of matrix B, number 4. And the result, as you can see, the original first row is now the first column, and the original first column is now the first row. So the matrices are related in that way. Matrices A and B cannot be added as their dimensions are not the same. If we try and do that, we'll get an error. Matrix A added to matrix B gives an error, a dimension error, because the dimensions don't match. Matrix A is 2 by 2, matrix B is 2 by 3. But matrix A can be multiplied by matrix B. since the number of columns of matrix A is the same as the number of rows of matrix B, and the result is a new 2 by 3 matrix. Let's look at how that works. Matrix A multiplied by matrix B is a new matrix, and we can store the result of the new matrix, labelled C, by tapping the Store button. And here's matrix C. Option number 5, you can see, is the result. However, matrix B cannot be multiplied by matrix A since their dimensions don't match appropriately. So if we try to do that, matrix B multiplied by matrix A, again we'll get a dimension error. The dimensions don't match in the correct way. Since matrix C was obtained by multiplying matrix A by matrix B, you might expect that A times B is equal to C. If you now divided matrix C by matrix A, again the result would be expected to be matrix B. So let's try that. Divide matrix C by matrix A, but we get an error because you can't divide matrices. But notice that we can get the result by using the inverse of matrix A instead of dividing by matrix A, as you can see on the screen. And so, to show you that, matrix A inverse multiplied by matrix C gives us the result of matrix B, as we would have expected, and as the screen down here shows. This is similar to what happens when you multiply integers. So for example, 3 times 7 is 21. And we could say that 3 inverse multiplied by 21 gives 7 in exactly the same kind of a way. So that's the end of our adventures with matrices. Students can use their class with their own matrices to see how the various matrix operations are defined and to understand the key ideas without becoming lost in the arithmetic that's involved. Later work by students will use the matrices for solving systems of linear equations. You will find that Module 7 of the ClassWhiz book contains information on how ClassWhiz can be used to deal with various aspects of matrices, including their use in solving systems of linear equations, as well as detailed explanatory text which can be copied for students as well as teachers. The module includes some exercises to check efficient ClassWhiz use, some examples of activities to suggest educationally valuable things to do, and some guidance for teachers. You can download this book freely from the Casio Worldwide Education website. Happy calculating!